So let's learn how to draw auxiliary views using the center plane reference method. Now this method is used to draw auxiliary views of symmetrical objects. A symmetrical part that is cut by an inclined plane results in a surface that can only be shown true size and shape with an auxiliary view. Now the example that we have over here is you have this hexagon which has 6 sides and it is symmetrical on this axis. So what I will be doing, I would be putting in my inclined plane right on the symmetrical axis and draw my auxiliary view. So now let's see how we would draw an auxiliary view using the center plane method. So the first thing that we have over here is a top view and we have a front view. We have to identify where is our inclined plane and what direction am I going to be looking at the object and drawing my auxiliary view. So if you look over here, this is our inclined plane and this is the direction that I will be looking at to draw my auxiliary view. So again, this is my top view and this is my front view. So I'll be drawing my auxiliary view parallel to this surface somewhere around here. So the first thing I will be doing is projecting my lines. You can see that over there. I can zoom in a little bit. So I project my lines from the front to the top. Then I project my lines perpendicular to my inclined surface. Then the third thing I'm going to do is put my center reference plane right here, which corresponds to this line right here. Now what I do is from the center I will be taking measurements and transferring it on to my auxiliary view. So I'm going to put a parallel line with respect to this surface, and again this is going to be my center line for the auxiliary view, which is the same as over here. Now the next thing I would do is put in numbering, so it makes it a little bit easier to number and see our objects. So I'm going to erase that right now just to make some more space. I'm going to call this edge as 1, this edge is 2, this is 3, 4, 5, and 6. Okay, now if I drop them down over here, this is going to be 2 and 3. This is going to be 1 and 4, these points, and this one is going to be 6 and 5. Okay, the center plane I'm going to be naming it as X and Y. Same thing over here, going to be X1 and Y1. The next step that we have to work over here is the distances from the center to these edges. We are going to measure those and transfer it from this center to our edges on this side. Okay, so let's do that. For that, I'm going to zoom in a little bit because this is where I'm going to put my dimensions or get my dimensions from here. Dimension from the center till this point is going to be called as D, and from the center to this point we're going to call it D again. Now to get edge 5 and edge 6, we will transfer D and D from here so we get those two edges. So let's take another edge that we would need is from this edge and from this edge. Okay, and we would call this as D1 and D1. So both are taken from the center of this reference plane. From the center to this edge, from the center to this edge where it touches the 4. So for this exercise, that's all we would need because we have this one taken care of, we have this one taken care of, we have this edge taken care of, we have this edge. These two edges are in the same line as 5 and 6. So now we have our same center reference plane parallel to our inclined surface. All we will have to do now is transfer these dimensions. So from here till here, I'm going to measure it as same as D. Same thing on this side. This is D. Okay, so which is 6 and 5. I'm going to make that reference mark right here wherever the arrow ends. Okay, so we already got this point and this point. Now to get 4 and 1, we will have to get from the center. Again, see, 4 and 1 is right here. I'm going to put a distance of point here and another one over here. Okay, so what do we have here is we have the number 6 here, number 5 here, this is 4, this is 1. These will go all the way back, the 6 and 5 till here. This will be called as 2, say 2 and 3. Now how did we get 4 and 1? If we use D1 from the center we go all the way till number 4, which is right here, and project that. This is going to be D1, and another D1 is going to be all the way up till here, till number 1. Okay, so now we already have all our 6 points. The next thing we need to do is just connect these dots to get our auxiliary view. So for doing that, I am going to connect the dots. There's 2 and 3, which is this one, 3 and 4, which is that surface, 4 and 5, that is this surface, 5 and 6, that's this one, 1 and 2, that goes that one, and 1 and 6, and now we have 1 and 2. So that completes our auxiliary view for this object using the center plane reference technique. Now again, you have to remember this will work only when the object is symmetrical, and that's what we have it on this axis. Now if I were to do another exercise for using the same center plane reference on this side, only difference in here is instead of a hexagon we have a perfect circle which we have to draw in auxiliary view. Now when we have a circle or a cylinder and that is cut at that angle, so first thing we identify the angle and we project it on to our auxiliary view. Now if I'm looking in this direction, it looks like a perfect circle. How would this circle look if I am looking in this direction, which is perpendicular to my surface for the auxiliary view? Would it look like a perfect circle, or would it look more like an ellipse? So the answer over here, it will look more like an ellipse. Now drawing an ellipse is not as easy as drawing a circle. So for that we will have to project a lot of lines, and then we have to connect these arcs to form our perfect ellipse. Now to do this, we are again going to follow the same exact technique as we did in making our hexagon. So first we identify the slope, the inclined surface. We are going to put a center line, which is the same as over here, and then we are going to project the distances. So right now I have the top, bottom, and the center projected. So if I turn my lines off, it's going to be a lot more clear to visualize it. So I have my reference lines going here from the front to the side view, and from the center I'm going to measure this distance and project it over here. So now let's project the center ones and see if that is enough. So I'm going to do my measurement. This is my front view. This is my side view. And this is going to be my auxiliary view. Okay. Now I'm just going to be drawing this surface. I'm not drawing the whole complete auxiliary view. I'm just drawing the auxiliary view, which is going to be a partial auxiliary view like you see over here. I'm not drawing this part, I'm just drawing the angular part. So let's go on with this one. First step is identifying the angle that we are going to look in. Second step, we do our center reference plane line here and here. The third step now is transferring the dimension. So I am going to measure distance from here till there as D1. Same thing from the center till there, center till this side, just like the previous example we did. D1, D1. Okay, so now if this point corresponds to that one, this point corresponds to this one. Okay, so if I were to draw arcs really well, that would already give me my ellipse. But the problem with that is we need a couple more points to be more perfect. So what am I going to do for that is I'm going to draw a couple more reference lines. So I will go to my view. I'm going to project a line from there, line from here, which is equidistant from the center. Okay, same thing over here. Now we got 1, 2, 3, and 4 more points. Now I will have to project these lines going in this direction as well, wherever it intersects. Okay, so I'm going to just select these lines right now and copy them rather than sketching it out, so it's more cleaner. So one goes right here, the other one will go right here. Now we do the same exact thing of measurement. We are going to measure, let me zoom in a little bit more. We are going to measure from the center to here. And the same thing on this side. There's going to be D2, D2, same thing on here, D2, D2. And from the center, I'm going to project the first one which is from here. I'm going to measure that distance. It's gonna fall somewhere over here. I'm going to measure that distance. It's going to fall somewhere over here. Same thing on this side and this side. So now I could go in and make more reference lines and project it and transfer it from the center if I would like to. But I'm just going to stop right here. But I could go in another one, make another projection here, make another projection here, same thing, transfer it on this side and on this side, so we get some extra points. Okay, so now the only thing that is left is putting in arcs and joining these dots. So if I go really slow and good, I would be able to get it. But using the pen that I'm using over here, it's not the easiest thing. But you would be using tools for doing the same thing. So this point is a little out of line, so I'll move it here. Okay, so this is what we have. So we should have a perfect ellipse. Now if you use your tools, you are going to get a perfect ellipse. So if I want it, I could project this edge all the way here and draw that and complete it as a complete auxiliary view. But that is going to be extra work, so I really don't care about drawing that. So all I'm doing is making my partial auxiliary view. So if I would like to put in my reference dimensions, it's D2, D2. Same thing on this side, this is D2 and D2. So I hope you understood how to draw auxiliary views using the center plane reference method. Okay, now we already have two examples over here that we did. One was for drawing this hexagon and the other one is for drawing this cylinder. So the next one that we are going to be covering here is going to be an example of dihedral angle. Now first thing we need to understand, what is dihedral angle? A dihedral angle is the angle between two planes. So if you look at this block over here, you have one plane and you have the second plane. So there is an angle between these two planes. There is that angle, and we need to determine what that angle is. So when we have an object that is cut in this angle, then it's tough to get the exact angle. Like for example, if I had this object right here, and if I had a dihedral angle, going straight, like going straight down instead of going at an angle. If it would have gone straight like that, then it would have been a lot more easier for me to measure this angle. But in this case, we don't have it going straight. We have it going at an angle, if you see over here. So the only way we can draw and get the perfect angle is by drawing an auxiliary view. So a dihedral angle is the angle between two planes. Determining the true measurement of the dihedral angle is a very common application for auxiliary views. Now let's see what we have over here. We have the top view looking this way, and we have the front view of the same thing, this object right here. Now to find these angles, if I would project it straight down, there's no way I could get the correct angle. So we use auxiliary views to find this angle. And to do that, what we have to do is we have to project our angles onto our auxiliary plane. So sometimes you might get confused how you are looking at the object. You're not looking that direction. You are looking in this direction now. So first thing I'm going to do is name these planes. I'm going to call this plane A, this plane B. I'm going to call this point, which is right here, and right here, as the number 1, and that is what I am projecting, and I'm going to get those distances from my folding reference lines. Okay, so that was my first step. The second step, what I do is I draw my folding lines, which is that one. Then I draw my other line, which is that one. Now you have to make sure that it is going straight and it is perpendicular. Okay, because what we are going to do is we are going to transfer dimensions. As dimension number 1, D1, and this dimension from the start till the end is D2. Now same thing we are going to transform from here to here, because this is where the object starts. So I'm going to have my D1 up till here, and I'm going to have D2 up to here from my folding line. If I were to draw a line, my object would start right here, and this edge would end from this distance to here. So my object has to fit in this much, correct? So I'm going to project this line, going to project this one, going to project that one, going to project this one, this one. Okay, now all I need to do is transfer my dimensions. So I will measure distance from here till here, which is going to give me D3, which is point number 1. Then I'm going to measure the same distance from the reference plane till here, which is from there till here. This is D3. Okay, going to project these lines, these edges. A is going to come all the way up till here. B is coming all the way up till here. We have point 1, which is right here. And now all we need to do is connect these. Once we connect it, we are going to get the perfect angle. So let's connect it. start from there till there, and I start from here till here. So that's the angle. If you look, it's different from what we have over here, and this is the correct angle that we got. Now let's complete the whole object. Now this was projected all the way from this edge, so I'm going to make a line from there till D2, which is from the reference till the end of the object. Actually, it's going to be from here till there. Same thing on this side, from here till there. We have the back side, which is from the reference till D2, from the reference till D2. I measure that from our reference till the end, and this is what I have. Then we have a line going from here till there. Now this is D1, from there till there. Same thing on this side. Okay, so that's our object. Only one line is missing for this edge, and I'm going to put that right in. Okay, so what we did over here is successfully made an auxiliary view to get the perfect angle between plane A and plane B, which is called as a dihedral angle. I can name this as auxiliary view. And this is the perfect angle that we just found. Okay, so this is the way you're going to draw auxiliary view for dihedral angles. The next one, the next exercise we have is a partial auxiliary view. Now we have already done a lot of these partial auxiliary view. So the only reason why we do make partial auxiliary views is because when you're doing hand drafting, you don't want to spend a lot of time on drawing the whole object. Secondly, when you are looking in this direction and drawing your auxiliary view, all the lines that we have are regular shapes because we are seeing it perpendicular. But now on the other hand, this object looks more like a 3D that you see over here in the picture, and it takes a lot of extra time to be drawn, which is unnecessary waste of time. So in that place, we will be using the technique for drawing just partial auxiliary view rather than drawing the complete one. This is a normal practice. Do not project features that are not part of the inclined surface. So if you look on this side, the inclined surface is just this right here. Okay, and this one is not part of the inclined surface in our auxiliary view, so that's why we don't need to draw it. Partial auxiliary view saves time and produces a drawing that is much more readable. The full auxiliary view is harder to draw, read, and visualize. Okay, so that's the reason why we draw partial auxiliary views. Now, when we were looking at this object, this direction, we are looking head on to this hole. So the hole will be drawn as a perfect circle. But when I'm looking on this side, even though I have a perfect circle over here, that is not right. You see what I'm saying? Because if I'm looking in this direction, I don't see it as a perfect circle. I see it more like an ellipse, which is the same example that we covered over here. So it'd be more like this shape and not a perfect circle. So this is the wrong example. So you see, it's going to take unnecessarily more time to be drawing that object. And that is why you don't want to make the complete auxiliary view. Yeah. Okay, now the next one is similar to the partial auxiliary view, but instead of even making partial, if the object is symmetrical, then you will just make half auxiliary view if you look over here. Now what does this do? It saves even more time than I would have spent over here if I were hand drawing the object. Now you have to remember, the object has to be symmetrical. So half auxiliary view symmetrical objects can be represented as an half auxiliary view. That is, only half the object is shown, like what you see over here. If I were to draw the full auxiliary view, then I would have had to go in and do the extra work of making those lines and those arcs and the circle. So this is good enough for me if I want to save time. And obviously I'm not even worrying about drawing this surface. Okay, so all we have to do is just have this much, and it explains what we are trying to tell. So are we understanding now? We understanding what is half auxiliary view, what is partial auxiliary view. Now this example that we had over here, remember, we made a full auxiliary view when all we needed was just this surface with a circle inside. So it makes life so much easier if we are just doing partial and half auxiliary views rather than full. The next topic we have is auxiliary views to determine the true size of an edge. Now how would we determine the true size of an edge? Now this is the example that we have here. This is the 3D of the same object. And if I'm looking at this, this is the top, this is the front, same thing, top, front. So when I'm looking on the top view, I'm looking in this direction, so I see this surface and this surface, which is this and this. I even see these two surfaces because they are an angle. If they were at a right angle, I wouldn't be seeing them, but now they are angled, so I will be seeing them. So what we want to find is the true size of the line or an edge. So I want to find the true size of this line, starting from there till here. What is the true size? Is that the true size? Is this the true size? See, when I'm projecting it down, what is my true size? It's tough to find out what my true size is unless I draw an auxiliary view to find the exact size. So the first thing I'm going to do is draw my folding line right here and right here. I'm going to measure my distances and project it. So let's number these. I'm going to call this number 1. This is number 2 right here. Number 3 right here, and number 4, just for us to understand better. I'm going to project number 1 right here. And we have a line joining 1 and 2, the edge, and that is what we need to find. But when I'm looking in the front view, I won't be seeing that line. If I'm looking in this direction, I won't be seeing that line because it's hidden. So I can always have a hidden line going like that. And if I number this, this is going to be 2, this is going to be 1, this one is going to be 3, and this is going to be 4. Okay, so now we have to start measuring our distances from the folding line. So if I measure from here all the way down till number 2, which is right here, is going to be D. Same thing, I will take from the folding line all the way up till that same distance. That's D. So what is this point that we just got? This is 2. Now we need to measure this distance from this point till 1, because we want to find 1 and 2, right? So this distance till 1, we're going to call it D1, and that distance is going to be the same from here till here, D1. Now this is 1 here, and the 1 is going to be plotted on this side. So all I have to do now is join 1 and 2. So this is the correct size or true size of line 1, 2. So did you see how we made this auxiliary view to find the edge or the line true size? Because again, in the top view you don't have the true size, in the front view you don't have the true size. If I were to make a side view, obviously it wouldn't be a true size. Now why it wouldn't be a true size? Remember, because of foreshortening. So the only way to do that is we have to find the angle that we want to make the auxiliary view for. I'm going to be looking in a direction that is perpendicular to that line, which is this one. I'll draw my reference plane, which is parallel to that line, and then just measure the distances and project it. So it is as easy as that. So these two distances are same from our plane folding lines. Okay, so that's the auxiliary view to find this shape for true size. Okay, now we have one more left, which is the last one for this chapter, and this is successive auxiliary views to determine true size of an oblique surface. So in the first one, all we were worried about is finding the edge and the line true size, which is just that line. But in this example, what we're doing is, instead of finding just the edge, we are going to find the true size of the oblique surface. Now the oblique surface is not at normal to any of the views, any of your principal views. Okay, so for this we will have to make two auxiliary views, and when we make two auxiliary views, they call it successive auxiliary view. So we start from an object, make an auxiliary view, and from this auxiliary view I'll make another one, and that would give me my true size of this oblique surface. So let's number our object. This is number 1, number 2, and number 3. So when we are looking in the top view, we have number 1, number 2, number 3. In the front view, when I project it down, this is number 1, this is 3, this is 2. Okay, so we are going to draw our fold line and begin transferring our distances from here to here. So we have a fold line there. We are going to draw the perpendicular to this line that we project for 1 and 2, because we are going to find that distance, and from this fold line I'm going to transfer my dimensions. For example, just like the previous examples, I'm going to call this as distance A. from fold line till 1. So from fold line till 1 is going to be right here, which is 2 and 1. So we already found the location for 2 and 1 from the fold line, which you can look over here. It's the same distance. Now we need to find for the location for 3 from the fold line. So if I go in here from my fold line, I'm going to try to get this distance, which is for 3. Now this distance that we measured is going to be called as B, and I have to project the same thing from the fold line till we get 3, which is the same distance as B from here and going all the way up till this dot. This is B. This is A. Okay, now all we need to do is just connect the line from 2, 1 till 3. This is 3. Okay, so we already got our first auxiliary view. Now I'm going to make another auxiliary view, but this time we are going to be looking in this direction, perpendicular to the angle. And our auxiliary view in this case is going to be projected like that. Okay, so let's continue that on this side. We already have 2 and 1, and this is 3. This is the angle we are going to look in, which is perpendicular to this surface, and make our lines, reference lines, perpendicular to this. So let's do that. That's 1. That's 2. I have to make my reference plane, which is going to be parallel to this. So that's my reference plane. Now the next thing I will be doing is transferring my distances from here to my points 1, 2, and 3, corresponding from here to my points 1, 2, and 3 in this direction. So remember, first we started using these and transferred those onto this one. Now we are going to use this one, which is this one, and transfer on our successive auxiliary view. So let's measure the distances. This is 1, this is the same as 2, and this is 3. Now I need to measure from my folding line till 1. So I have to get this distance from my folding line till here. So I'm going to call this one as C. I'm going to transfer that from here all the way up there. This is C, and make a line like that right now, really light as a reference. So with C I already got 1, which was this. So my 1 is going to be lying somewhere there. Now I need to get 2 and 3. Okay, so if you look, this is 1 and 2 that was projected here. So 1 has to lie somewhere here. So if I project this line all the way up, this is my point number 1. Now I need to find 2 and 3. I know 3 is going to be lying somewhere on this side. So let's measure 3 from our folding line. It's going to be that distance from there till here. I know there's a lot of lines and it will get confusing, but I'm pretty sure you should be fine. So C, this we are going to call it as D, and D is going from folding line till till 3. From folding line, this is 3. I'm going to make that distance. This is going to be D, and 3 is right here on the same surface. So we have line 1 and 3, so I can already go join this one if I want, but let me find line 2 or point 2. Now if I look over here, 2 is lining up somewhere over here with 1. I need to get that distance, so let's get that distance from here. And 2 is we are going to call this as E. From the folding line I measure up, and this is where I got my E. My 2 would be right here. It should be in the same line as this. Okay, so now let's join our dots. 1 and 2, it has to be in the same exact line as this. 1 and 3, and 2 and 3. So if I number that, this is 2. So 1, 2, and 3, and this is the true size of an oblique surface, which is 1, 2, and 3. So this is the surface corresponding to this one. Now again, why is this called as a successive auxiliary view? Because we started from the top, the front, made an auxiliary view, and we used this auxiliary view, made another successive auxiliary view to get our oblique surface with the true size. So this pretty much finishes our auxiliary view chapter. I hope you understood what everything we have in here and everything that we covered. I know auxiliary view can be a tough chapter sometimes because it's not one of your principal projection views. so it does confuse a lot of students, but I'm pretty sure when you go through this lecture it will clear all your ideas. Okay, so this is Tutor Ali, and I will see you in my next class where I will be covering the chapter for dimensions. Thank you for listening.